All right, everyone. So it is 7:05. I think it would be a good time for us to begin. Um, Thank you all, first of all, for coming here today to listen to this symposium. Basically, this symposium, which is our second one, is going to be about chemistry as a cornerstone of the modern world. This is kind of a continuation of our last one, which was about the chemistry Olympiad and how to do good on it, how to practice for it. Basically, a lot of tips for that. But in this case, we're going to be going over something I think a little bit different. Our special guest speaker here is JiaXu, and basically, he's going to be presenting for you today. And basically, the first thing, well, first of all, our agenda for today is to introduce our guest speaker, then to present, and then we'll have a quick Q&A before we end for today. I don't know how long this will take, but probably around, if not less than an hour. Yeah. So first of all, the introduction. So our guest speaker, JiaXu, is basically very, very qualified for his job of kind of going over and talking about chemistry, especially. He was a U.S. National Chemistry Olympiad, U.S. NCO national finalist, which meant that he was top 20 in the world or in the nation. And then he was a 3-time American Invitational Math Exam qualifier, also known as AMY. If you live in the US, it's pretty well known. He was also a Science Olympiad state champion, and he was also a National Merit Scholarship semifinalist. So yeah, that's pretty impressive to say the least. So without further ado, I think it would be nice for us to get started. If you guys have any questions that you have, please don't speak up in the middle of class, not the class, but in the middle of the presentation. If you really want to, if you don't want to like forget your question, please type it into the chat. So that way we can get back to it later, because afterwards, after the presentation, we'll have a Q&A, question and answer, where we'll be able to answer your questions on anything that he might have talked about. But other than that, I think it would be fine for us to go ahead and get started. So remember, again, if you have any questions or you think of any questions, please just type them into the chat. We'll get to them after presentation. So yeah, would you like to begin sharing? Let me stop sharing.
Okay.
Yeah.
Yeah.
All right. Yeah.
Mm-hmm.
Oh, you might want to share a slideshow. Click slideshow there.
Yeah, I will.
Okay.
Okay.
All right, nice.
Okay. So hello everyone. I am JiaXu Liu, and my topic this week is chemistry as a cornerstone of the modern society. So first, the first point that I want to talk about is how chemistry detailedly explains what we see. And then I will show that to you through 3 everyday phenomena. The first one is rusting, which I believe that most of us here have witnessed his or herself. So rusting is just what happens when object made of iron comes into contact with water and produce rust. So as you can see in this picture, the over time the iron products turns brown, and the brown thing on the surface of the iron product is essentially rust. But why? Why does iron product produce rust when it comes into contact with water? To answer that question, we will need some chemistry. Here, as you can see in the picture, we have some illustration of the chemical processes happening in between the water and the iron. So first, in water, we know that in water there's always a certain amount of oxygen, and the oxygen, when coming into contact with iron, will interact with the iron, and then together it will go through a process named the redox reaction. And what that does is it reduces oxygen and in turn oxidizes the iron. So then when oxygen come into contact with iron, the iron becomes oxidized by oxygen. So the solid iron will first turn into iron 2+, and then subsequently it will turn to iron 3+. And then as iron 3+, it will form an oxide with the reduced oxygen and become Fe2O3 or iron 3 oxide. And the color of iron 3 oxide, or in general, any iron 3 products, is brown. So essentially the rust that we see is just iron 3 oxide. Okay, so that's how rust forms, and hopefully through this first example, you can start to get an idea of how chemistry really explains what we see, what we observe. Okay, here's my second example, greenhouse effect. This one, I believe every one of us have heard of it in some ways, either learned about it at school or went online and read about it. So you may or may not remember what it actually is, but it is what happens when greenhouse molecules such as carbon dioxide, methane, and nitrous oxide absorbs heat and blocks the heat from exiting the Earth's atmosphere. So as you can see in this picture, the heat gets emitted from the sun and passes through the atmosphere into the Earth. But then usually without the excessive amount of greenhouse molecules, it is able to go out of the atmosphere the way it came in. So then the heat is in a way preserved inside and outside the atmosphere. But here notice that because of industrial revolution, we have more and more greenhouse gas emission. So then these greenhouse molecules get scattered around the atmosphere. And what it does is that they absorb the heat that try to get out of the atmosphere, and then essentially they trap the heat inside the atmosphere or on the surface of the Earth. But then the question comes, how? How does the greenhouse molecules trap heat? Why are they capable of absorbing heat? So to answer that, we again refers to chemistry. So here, this is a picture of the vibration inside a molecule of CO2. The first two on the top are stretching vibrations, and the bottom two are bending. And here, as you can see in the picture, each of these vibrations correspond to a number. This is called a wave number, and that determines what wavelength of light is absorbed by this mode of vibration. And through the caption, you see that among the 4 vibrations, 3 of them are IR visible. That means that they're capable of absorbing IR light or IR radiation. And we know that IR light is actually the major source of heat. So what it does, because it is IR visible, it absorbs IR light, and in other words, it absorbs heat. So because it absorbs heat, as you can see in the picture, the heat is not able to go out as usual. And then what ends up happening is it's get emitted from the greenhouse molecule in all directions, and part of it get back into the atmosphere. So because as the number of greenhouse molecules increases, more and more heat gets back into the atmosphere instead of going out of the atmosphere, and that end up making more and more heat getting trapped on the surface of the Earth and causing global warming, essentially. Okay, so as you can see in this example, the chemistry explains how heat is actually absorbed by the molecules. And it is only through actually knowing how it works, how heat is absorbed, that we can try to find solutions to the phenomenon. Because if we don't even know how it works, how will we be able to prevent it from happening? Okay, so this is my second example. And my third one is ocean acidification. This one might be less familiar to you guys, but it is when there's an increasing amount of CO2 emission, the ocean becomes more and more acidic, as you see in this picture. But why? Why does CO2, why does carbon dioxide makes ocean more acidic? So here again, chemistry. CO2, when it enters water, so CO2 in gas is a separate molecule, but when it enters water, it combines with a water molecule. And then what it turns into is carbonic acid, or H2CO3. And then as you can pick up in the name, carbonic acid is an acid. And if you have already taken a chemistry or biology class, you know that acid would release H+ ions, which essentially reduces pH and increases the acidity. And when more and more carbon dioxide enters water, more and more carbonic acid will get produced, and more and more H+ ion will get released. And essentially, when it reach a really large amount, it will be really bad for the fish and other creatures in the ocean. So this is how carbon dioxide creates an issue not only for global warming, but for the oceans as well. Okay, hopefully through these three examples, you can see how chemistry really explains what we see, what we experience from a fundamental level, and allow us to understand our world better. So then what does chemistry do besides explaining what we see? In my opinion, it is also a great tool to make what we want. It is what we use to make our life more efficient, more convenient. So my first example is how we use chemistry to create energy. And in my opinion, one of the best example for that is batteries. Battery is probably one of the major power sources nowadays, whether it is your phone, your computer, your watch, or other electronic devices. All of them would have to use a battery of some sort. So, and as you might already know, battery is a product of chemistry, and we'll talk about that in more details. So there are two batteries that I want to talk about, and they're all pretty significant in the history of battery production. The first one is lead acid battery, and it is actually the first rechargeable battery, meaning that you're able to recharge it after power is depleted, and then use it again, so that you don't have to throw it away every use. So here's a picture of the lead acid battery, and you can see there's a lot of components to it, and there's a lot of layers, and these layers are actually electrodes. And there's the blue part, I believe, is just water serving as the solution, or actually it's a solution, diluted solution of H2SO4. So that is sulfuric acid serving as the solution that conducts electricity. Okay, so how does it work? This is a depiction of the galvanic cell inside a lead acid battery. As you can, I'm not sure if you can see, I'm not sure if everyone understands it, but I'm sure that you will after taking classes like AP chemistry, because this is the galvanic cell is a pretty big part of the class. But here, what it means is that here you notice that one of the electrodes is lead and the other is PbO2, which is lead 4 oxide. And you notice that on the top, there's an arrow with E-, which is electron, meaning that electron is getting transferred from lead to lead 4 oxide. And why is that? For people who already study chemistry, you know that lead 4 oxide is at a very high oxidation state. and it wants to get reduced into lower oxidation states. And on the other hand, lead is on a lower oxidation state and it wants to get to a higher oxidation state. So then these two, when these two come together, the lead will want to give away its electrons so that it can get oxidized, and then the lead 4 oxide will receive electrons so that it can get reduced. So then that creates a flow of electrons that powers our devices. Okay, so that's pretty much the mechanism of lead batteries. And in this picture, you can also see other details such as the transfer of H+ ions. And you can see on the top, there's a number 2.1 volts, which is pretty big, but not as big as the next battery that we're going to talk about, the lithium-ion battery, which is much more efficient than the lead battery. Although the lead battery is already pretty efficient, the lithium battery is even more efficient. In fact, it is one of the most efficient batteries that ever existed, and it is still commonly used nowadays. Here's a picture of the lithium battery. And here's a picture depicting the mechanism inside the lithium battery. So pretty much it is the same as a lead battery. It involves the transfer of an electron from a lithium ion to the cathode, which is aluminum. Okay, so and you may wonder why lithium ion is more efficient. This is partly because lithium, is the most reactive metals. So lithium ion has the reaction between lithium and lithium ion has a really large potential, and that increases the electric potential between the anode and the cathode. And that is what increases the efficient or the amount of energy that's being stored inside one lithium battery. Okay, so besides energy sources, you may wonder, is there anything else that chemistry is particularly useful for? And of course, medicines. And here, the example that I gave is aspirin, which I assume that most of us, or if not all of us, know what it is. Hopefully you never had to take on one of those, but it is used to relieve fever and pain. And it is one of the very common medicines nowadays. And it was actually developed in 19th century, I believe, and it's still used nowadays. So you can see how powerful this medicine is. And in my opinion, it is a very great example of the vital role that chemistry plays in medicine discovery, because obviously aspirin is not a naturally occurring compound, and it is actually synthesized through a reaction of salicylic acid and acetic anhydride. This a chemical product from these two compounds. And as I mentioned, it is used to reduce fever and relieve pain. Here's a picture of the aspirin. And here's the reaction that's used to produce aspirin. This is the reactant on the left is the salicylic acid, and reactant on the right is the acetic anhydride. And I believe that it's through some sort of coincidence and some sort of luck that the scientist was able to actually produce a useful compound from these two. And as you can see in this example, it is only through chemistry, through knowing how chemicals react, that we are able to come across a useful compound like this, like aspirin. And there are many other medicines produced through chemical synthesis, and it is only through a great amount of chemical work that scientists are able to develop such mechanisms and are producing these life-saving medicines. Okay, my last point. So obviously chemistry has already done a lot for us, for humanity. But what I want to say here is that chemistry is developing to be better. It is developing now to be more eco-friendly, meaning that it's transforming to become more friendly for our environment. So how specifically is it undergoing that transformation? It is through the subject of green chemistry, and I call that our future. So green chemistry is a recently developed subject, and it's slowly but steadily gaining more and more attention worldwide nowadays. So what does it do? One of the major things it does is to find replacement for hazardous chemicals. Because as you know, sometimes in order to produce certain products, we need to use some very hazardous chemicals such as heavy metals. Sometimes we need those for catalyst. And what the green chemists do is that they try to go to find replacements for these chemicals. For example, sometimes like if we have to use metals like lead as catalyst, these scientists try to find replacement for lead. For example, if they can try to find naturally occurring products, and if they can substitute that into the reaction and it still works, then that will obviously be better for our environment. It will obviously be less harmful. And that is essentially what they're trying to do. They're trying to maintain the reaction, but replace the reactants or the catalyst with more and more environment friendly substances. And then here are some examples of green chemistry or progress that we have made in green chemistry. So first is biodegradable plastic. As you know, the traditional plastic that we use is not biodegradable. If you put it under the ground, if you just bury it under the ground, it will not decompose even after hundreds of years. So what the green chemists try to do is they try to create biodegradable plastics that have essentially the same functions as plastics, but they're instead biodegradable. So then we're able to we're essentially able to destroy these wastes and prevent them from harming our environment. And another example is the metathesis reaction, which I show the picture here. And what it does, it might not be obvious from the reaction itself, but what it does is that it significantly reduces the energy needed to carry out the reaction. And then it has the potential of reducing the amount of greenhouse gases produced in many of the major industrial processes. So that obviously will be very, very beneficial for our environment, and that can help us solve issues such like global warming. So hopefully you can see that's the direction that many chemists are heading right now. And yeah. Okay, so this is pretty much what I have for the how chemistry is closely related to our society. Does anyone have any questions?
Well, I've got one. So I was thinking about what you were saying regarding like how chemistry is used a lot in our batteries, and everything like that in medicine. So I've been doing a lot of reading on nuclear energy, like nuclear power, as opposed to other sources of power like fossil fuels or solar energy, stuff like that. I want to know, since nuclear, power is very, very important, and very, very chemistry related, since it is, a chemical reaction producing that energy. I want to know what's your opinion on that, right? It's very controversial because it can be very unsafe. And, of course, we know that things have happened, right? Fukushima,
Yeah.
we've had Chernobyl.
Yeah.
So I kind of want to know, do you think nuclear energy is good? What are some of the pros and cons, like the good parts and the downsides of it?
Yeah, I would say that nuclear chemistry is indeed it is very efficient. It is definitely more efficient than just using the fossils, because also it's low cost, because you only need the several atoms such as like uranium. You only need those, and those are usually easier to obtain and then process than the fossils. But like as you said, it creates more harm than the traditional energy sources,
Mm-hmm.
and it's a greater risk. But in my opinion, if it's controlled correctly, I think it can be a good thing for the human being. But again, if it's like used in those wrong ways, like used to, for
Mm-hmm.
example, create weapons of mass destruction, and if it's like not controlled properly, such as the nuclear leakage that happened in Japan, then that will be turned to a harm.
Mm-hmm. Okay.
So yeah, there's like, in my opinion, there's like risk coming with greater efficiency, and that's pretty much true across all fields of science.
Fair. That's fair. So yeah, I guess it is really hard to say which one's better, which one's worse. But it's definitely something to think about. Does anyone else have any other questions? iPad, do you have questions? You're unmuted, so I can't tell if you're trying to ask or oh no, iPad doesn't have a mic. That's the thing. Okay. I don't know if they're connected to the audio or not. That's fine. All right. If no one else has any other questions, well, first of all, I do suggest that you do ask if you don't have any if you do have a question, because this is your best chance to get it answered. But otherwise, I think that was, again, pretty helpful, right? It kind of gives you gives you really good insight into how much chemistry is used in our modern world and where it's used. So like the aspirin that you get over the counter from Walgreens, that's a lot of chemistry into it. And like the batteries that we use to power everything, really a lot of different things, like more than you can name. Those things that we now know in our lives are powered by chemistry. So I think that was really, really good. Really good insight, great presentation. So thank you so much, for presenting. But I would say if no one else has any questions, then I think we basically are good to end the symposium right here, right now. But if you guys do have questions, please speak up. Other than that, thanks for coming. Really appreciate it. And we'll let you know about the next one. And